Well, good morning. All right, I'm out today because I'm hanging out with my daughter and her fifth grade classmates at JA Biztown. I know a number of you went through that process, and I'm looking forward to it. Chaperoning fifth graders. It sounds exciting, but there is a reason why I love teaching high school so much. There's a little bit of difference of teaching method, but I think it'll be really fun, and my daughter is excited, which means I'm excited. This is where we're starting today. We're going to do the 12 basic functions. It's in your note packet. If you find some weird order of things, you know how it went yesterday. There's a couple file differences. We're trying to reconcile these, but some files, like the one I've downloaded here, or taken pictures of, I hope it's the same as yours. If not, just patiently one, ask to pause the video. Second, just get there, and then when everybody's in the same place, just go with it. But I think it's okay. Just see what you can do. Linear function, one everybody knows and loves. We're going to talk about key features of these, because what happens, ultimately you want to be able to hand sketch these and then move them around, shift them around. So just the ability to sketch it just basically is important, because you can do the transformations, move this around, and then the way you construct it is the same no matter where it's placed on the graph. So you guys know a line is up 1 over 1 from wherever it's located, and that's the same line you've always known. Domain and range in this case, you can put in any x. It goes all the way to the left, all the way to the right for the domain, and all the way up and down for the range. Then if you go to and remember that these look the same, but they represent different things because of the context they're in. Domain is x values, small to big. Range is y values, small to big. Remember, you always put the smaller number. A bigger negative number is a smaller number, and I know that's a really common mistake. I know you guys are doing practice problems with domain and range, and sometimes you'll put, for instance, if it's between like -10 and 2, +2, a lot of times those will get switched around because you think, oh, small number on the left, big number on the right, but a bigger negative number should go on the left. It's the smaller number as in on the number line, more negative. All right, to the next one, quadratic, you know and love. X squared is the function. Domain on that one's all real numbers. It goes left and right all the way. And then up and down, though, this range business, take note, it does touch at 0, 0. And somebody asked that question yesterday. Does it touch there? That's the right idea. You want to know real details like, does it touch at a particular spot or not? Because it has everything to do with your range, if it's going to include a bracket or not. And this one does. So that's the range of that one. Good old cubic, x cubed. Everyone remembers this one too, kind of that snaky graph. It's all real numbers for both, -infinity to infinity in both cases. Okay, if you need pausing, go for it. I know I'm talking fast. I've also loaded the video up to Google Drive, and it's on my YouTube channel, etc. Okay, but we're going to cruise on. The next one is, let's talk about key features of these. So on the linear and quadratic, I pointed out some of the key points you would need to freehand draw. Linear, pretty known, up 1 over 1, just plotting points at a slope of 1. The quadratic, it does touch at 0, 0. And then from that, we call that the vertex. And so once you know the quadratic's vertex, then you can move over 1, up 1 to plot a point, and then over 2, up 4 to plot a point. And that's not a slope issue. Remember, we're squaring the number. So 1 squared is 1, 2 squared is 4. That usually is enough to get a decent sketch of a quadratic. And then the symmetry of it means you can do duplicates on the other side. You can always just graph one side of a quadratic or plot one side, then go to the other side of the axis of symmetry and do 2 more, or more. You can do as many points as you like. Let's go to the reciprocal function. This is where I don't know if your notes are in the same order, but find it somewhere. Take a second to do so. It's 1 over x. This one has all kinds of cool stuff. We do a whole lot of rational function work, not too long from now, and we'll talk about vertical asymptotes whenever you divide by 0. In this case, x can't be 0, and so there's a vertical asymptote whenever there's a value of x that would cause you to divide by 0. So there's 1 and 1 over x, this reciprocal function. Then if you take and do the domain, it's broken up by that vertical asymptote. So the domain isn't -infinity to infinity. You have to go -infinity to 0 parenthesis, because it doesn't touch it, and then that union symbol, parentheses, 0 to infinity. If you started the My Math Lab related to this, you'll start writing domains with the union symbol and all that. Oh, it's a pain, but use the help there. Ask me for help, whatever you need. Range on this one also broken up, but by something different. It's the range of the reciprocal function is broken up by a horizontal asymptote, which Sometimes the graph crosses horizontal asymptotes. Never vertical asymptotes, but sometimes horizontal asymptotes. This one has, you can see the domain. We're going off the graph, and that's kind of part of the deal, is can you read these known graphs and recognize their domains and ranges. Radical functions next, square root of x, call that a radical. Then the domain, it does touch at 0, 0, because you can put 0 into a square root. Square root of 0 is 0. So it does touch there, and that means it's a bracket 0 to infinity. And range, same thing. Starts at 0 of a height of the low height of 0, and then goes on up. Looks like it might taper off, but it doesn't. It just gets bigger and bigger. Okay. Absolute value, there it is. There's the absolute value markings. Don't forget on your calculator it's math num abs, because nothing numbs the abs like a little math workout. I had one this morning getting ready for you guys. It was awesome. Domain, negative infinity to infinity. And then range, it does start at 0, and then it goes up from there. So there's a bracket. All right, again, ask for pause as needed. I'm going to keep rolling with my ninja writing. If you notice how fast I can write, it's usually 2 or 3 cups of coffee, and I am good to go. Look at that. I put in a blue horizontal asymptote on the reciprocal function because I want to talk about key features of these and how to sketch it by hand. The reciprocal function is kind of centered around the origin 0, 0, and then there's these 2 asymptotes, vertical and horizontal, and then if you go from 0, 0 over 1 up 1, you can plot 2 points. After that, you just kind of let the graph bend and squish into each corner like that. It's a rough sketch. So when we do them by hand, we're going to do very sketchy sketches later. The things you want are the 2 vertical asymptotes, a point that's kind of like over 1 up 1 in both corners, opposing corners, and then you just kind of bend it into the upper right and lower left quadrants like that. Okay. Then when it comes to the radical graph, you just do 0, 0, and then from there you go over 1, up 1, and then over 4, up 2, knowing that the square root of 1 is 1, the square root of 4 is 2. Those are good, easy starting plot points to work with. And then on the absolute value, it's got slopes of 1 and negative 1 on either side. So notice those things, because when you're freehanding it, you're going to think, how can I recreate that graph? What do I need to remember to get a decent sketch? And those are the things I'm highlighting there. Okay. Next, exponential. Hopefully that's the order of your notes. I have no idea. E to the x is standard. Sometimes it's 2 to the x. It could be any base to the x. And so let me add to that. It could be, 2. Whoa. Highlighter's not going to help. 2 to the x is an exponential. 3, hey, any base number that's to the x power, that'd be considered an exponential. E to the x is just your famous Euler's number, and it has cool properties, and we'll talk about that later. Domain, left and right all the way, any x is possible. However, the range does 0 to infinity, not including 0, so there's a parenthesis there. It does start at 0. There's an asymptote, horizontal asymptote, and exponential functions are always positive. That's another cool feature of those. We're going to go next to logarithmic. We can do log of x, which is base 10, or ln of x, which is base e. We'll elaborate on that later. You may remember. They look very similar for our sketching purposes. You won't need to worry about what the difference is sketch-wise at this point. Domain, it starts at 0, doesn't touch 0. There's a vertical asymptote, and that actually becomes its key feature with a logarithmic function has a vertical asymptote. The exponential has a horizontal asymptote, and we want to remember that. The range on that one, it does go all the way down as you get closer to the y-axis. If you kind of peek in there, it does get really snugly up against there, but the graph just keeps going down forever. And then it goes up forever. So that range is all real numbers, negative infinity to infinity. The domain, though, 0 to infinity. Make sure you notice it is not a bracket. It doesn't touch there. Okay. Cool thing about these two is they are inverses of one another. That's what makes exponential and logarithmic. So if it's e to the x and ln of x, those are specifically the ones we use a lot. They are inverses of each other. Okay. They undo each other algebraically. Actually, I'm going to write here, inverses undo each other algebraically. So we'll use them to kind of solve in equations with logs and exponents. We use one to undo the other. But graphically, what's cool about them is they're mirror images of each other over the line y equals x, the linear equation that we started with. That's something we can elaborate on later. But they also, if you remember when you do an inverse function, do you remember you swap x and y and solve for y? I know a number of students remember that from Algebra 2. You swap the x and y coordinates and solve, and you get what's called the inverse function. Well, that's what these are. You would swap x and y and solve, and when you swap x and y, you're also trading the domain and range, which tells you about what x's and y's are possible. And things all kind of, everything about x and y trade. Instead of a vertical asymptote, we have a horizontal asymptote, and vice versa. We have the domain and range swap. So inverse functions are neat that way. They swap their x and y stuff, and they undo each other. Last one on that line is a logistic. This is one form of it that I've written there, 1 over 1 plus e to the negative x. There's a couple other ways to look at it. My favorite is lice minus licht. I'll tell you about that later. Then negative infinity to infinity, domain left and right is infinite, and there are two asymptotes, two horizontal asymptotes in this that the graph snuggles with. And so with my range, it goes between the asymptotes, which is 0 to 1 in that first picture. But sometimes, I threw in the other form over there. You can take a second to look at it. The other form is very similar. It just has an L on top and some other variables inside there, but it's more similar than you want to think it is. It looks crazy, I'm sure, at this point. But the L on top actually has to do with where the top is, where the upper bound, the growth constant up here, that L would be wherever that top horizontal asymptote is located. And that's a neat feature about it, is whatever number you put on top of this function tells you where the top of that logistic curve is, a S on the side. This is used for population growth, because you all may have, I'm sure you've learned in some biology class that populations grow exponentially, which this graph has that behavior, but it grows exponentially until they, whatever it's needed to sustain that population, food and other resources, are depleted, and then that population will cap. They can't go beyond the resources available to that population. Logistic is a way of modeling that. So sine and cosine, oh, you know these. These, I'm sure you have dreamt about the day these would come back. Sine, it starts at the origin and goes up and down. And then it's all domain, all real numbers, but the range, it goes between -1 and 1. It does hit at those heights, so there's brackets involved. Cosine is a little shift left or right of that sine curve. Same domain and same range. They're just, really, sometimes there are folks out there that never use both. They just stick to one, but they have cool properties, so we like to see both. There's the floor function, the step or the integer function. All of these are descriptors of this last function here. I like when I call it the step function because that's what it looks like. Floor function, integer function. On our calculator, if you go math and num, instead of working the abs, if you work the int part of you, you go down, int is a way of doing the int function. So your calculator will graph this. If you go to math num int, and then put an x inside the parentheses, it'll graph it for you. If you want to play with that, go for it. But it's got this little, it's kind of like brackets without a top around the x is how it's written. Its domain is all real numbers. You can put any x in there you want, but the range is goofy, right? There's lots of gaps. So we actually call it the integers. The range is, it touches all integers. That's a little Zorro symbol. That's the z with an extra back in the middle is called the integer symbol. It means all your negative and positive counting numbers. Okay, now we're going to test your skills. I'm sure you've got this. What kind of graph is that? Feel free to pause the video, throw out some ideas. Ready, 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 and of course it's a quadratic. Want to try the next one? What's that? You know this one, right? Cubic. I feel like I'm Daniel Tiger's neighborhood at one of those kids shows. You go, which one's the absolute value? Point to it. Right, the one, yeah, that one right there. Good job. It's an absolute value function. Good. Someday maybe we'll do a whole class that way. That'd be fun. Or not at all. There you go. Logarithmic. This one's hard to see, but there is the logarithmic. One of its key features is the vertical asymptote that you see now at -2 because it's all shifted. But you just have to know the general shape. So we're in stage 1. Can you generally see the shape of these graphs? And generally, we'll move them around and sketch them. Okay. Sine x or cosine of x, that one on the left there. Yeah, you knew it, but it could be either one. It just depends on how you shift those graphs. Do you know the next one? You see it? You see it? Can you see it? Square root radical graph. And then we got ourselves a logistic graph. Right. And finally, you know that last one. totally reciprocal 1 over x. Now, the 2 boxes below are you to go ahead and try and summarize which graphs have domains of all real numbers, of all these that we've gone through, and which have domains of all, ranges of all real numbers. What you want to do is to kind of categorize these, get yourself pattern behaviors and things like that. I'm going to let you do that on your own time. Pause now if you want. We've been in exactly 15 minutes according to my recording. But I'm going to keep rolling. You guys can manage the stop and start as you need. The next piece, piecewise, there's a shirt right there. Do you want a piece of me? I don't know if that's enticing enough. Would be better if I drew in some features of that graph. Yeah, do you want a piece? Of course. Yeah, we're going to move on. Then there's this graph here. We want to talk about if I have 0 to 20 shirts. Piecewise functions are a couple of my favorites. They're actually more realistic, more useful sometimes than a lot of other graphs. They're for categories. So for instance, 0 to 20 shirts, $25 each. 21 to 23, 21 to 30, 20 each. The more you buy, the less they cost. This is actually how they do t-shirts, by the way. That's how they're priced by category, by a band of quantity. So there you have it. If I do those bands in there and then I do those various prices, this is a great idea of a piecewise, because from 0 to 20 shirts, you have a particular output height of $25, and then 20 to 21. Notice the holes I put at 20, 30 respectively. It's because you notice it doesn't include that number of shirts. Like 20 shirts is for $25. I had to put a hole on that line I drew from 20 to 30 so that you know that you would have to jump up to the next line. So it gives you an idea, just a pictorial representation or a somewhat applicable situation where this is. And yes, I actually used this because we did some t-shirt ordering, and I have a project that I may or may not offer you guys about t-shirts and demand and revenue and cost and profit and stuff like that. Okay. To the next page, hang in there, pause if you need to. I wanted to show you piecewise functions are taking 2 functions you know the equation of, like 2/3 x minus 1 is that left-hand function, and then there's negative x plus 3 is the right-hand function. But we consider the whole thing, both of them is considered f of x, the piecewise function in question. So what we do for a piecewise function is that you have to be more descriptive, because you can say to somebody, hey, my function is 2/3 x minus 1 and x plus 3. And they go, which one? What do you mean? So you actually say, well, those are the 2, but you have to specify when they occur on the graph. And if you think of the x-axis as like a timer for as you go left to right, when do you see the graph of 2/3 x minus 1? Well, whenever x is less than 0, of course. That's when I see it. When do you see the graph of x plus 3? Exactly. Do you see them at the same time? No. I see it when x is greater than or equal to 0. You guys notice the dot? So at x plus 3, there's a solid dot. Okay. That's the idea, is that the what and the when, you have to have those 2 parts. There's no graphing of the when part. It's just helping you decide when do I see which graph. They're chopped up pieces of graphs that usually we draw the whole thing of. Now down below, we can do that here as well algebraically. If I don't even graph it, then what that means is when somebody says f of negative 4 and f of x happens to be a piecewise function that you see above there, you think, do I put negative 4 in all of them? No. You never put an input. So if you have a piecewise function, your input never goes into all of them. It has to specifically go on the right part, because like with the graph of it, negative 4 would only land on one of those 3 graphs in that particular piecewise function. Which one is it? Well, that's where the when, the domain of those x's over there, helps you decide where to put it. Well, negative 4, if you look at it, falls into that first category when x is smaller than negative 2. So that's the f of x piece we're going to put it into. Not the other ones. Don't put it anywhere else. Just use that one. So the next one, and you get out 0. The next one is input 6 into the function. Well, that fits that last category, x greater than 3, so you use that radical portion of the function, get a value, in this case 3. The negative 2, can you see it? This one's, now, you can reuse all of them over and over again. It's not a one-time deal, but it fits the top one. So negative 2 is that equal sign, and the less than or equal means we're going to plug it into the top 2 plus 8 portion of that function and get 4. The last one is 0 falls into the middle band from negative 2 to 3, so we're going to use that x squared minus 3 portion of the function. So you have to be really careful. You're only going to use one portion of the function when you have an input into a piecewise. and then you get the output. It's like the t-shirt problem. Hey, I want to order 25 shirts. What price do I pay? You don't pay 3 different prices. You just want to know which height do I go to. In this case, instead of having a graph, we have an equation that'll give you the right result. You're welcome to graph them if you like. Hey, speaking of, let's do that. So I think the next problems that we have, if we flip it over a little bit, actually there's one more down below that you get to try. Should we try that last one? Sorry, I left that off. If we try that next piecewise function, different functions, notice that. We're putting 8 in. Find out where it goes. Do you see it? Do you see it? Yeah, it goes to the bottom one, things that are bigger than 5. All right, try the next one. 0. Where's that one go? Where's it fit? Are you seeing it? Are you seeing it? Top one. Yeah, where x is less than 1. Okay, and then finally 4 is tricky. It's somewhere in there. It's somewhere in the middle band. Got it. Now this one's goofy because f of 4 falls in the middle, and you get out 3. And it sounds funny because I can't even substitute 4 in there, and that's fine. Remember, that's just a horizontal line, y equals 3. So when you put 4 in, the height output is going to be 3. Anything you put in between 1 and 5, any number of inputs, is going to give you an output of 3. And that's okay. So, and then the last one, hey, 5, where does that fall? Greater than or equal to 5 includes 5, so we're going to put it in the lower of the 3 piecewise functions. And so 5 minus 2, 4 it is. Last, and certainly not least, we want to do the graphical version. So this is where you can take and use the graph to plug things in, like 2 into that left-hand function. I plotted the point there in red. This is all color-coded. It's -1. What about at -3? Now this is tricky because there's 2 pieces of the graph at -3. The whole, it means it doesn't exist at that point. So you have to go you always find the solid dots. When you're substituting into a piecewise function or anything that jumps around, you're looking for solid dots. So 2.5 is the solid dot. You don't want to put 1 because that's a hole. Then you got -1 does not exist. I put that in there because notice that at -1 there's 2 holes. There's no graph. It's like it doesn't exist there. See, I don't know. And f of -4 is way over to the left. Go up, hey, there's a graph there. And then you just find the height that is associated with that. So it's 2, and I marked it in orange. All right, again, have pauses as you need. I know it's fast. I know this goes really quick for you guys. My ninja writing is it just, if you want to grab a couple cups of coffee and catch up with me in your ninja writing, you're welcome to. The Keurig just might need some water. So the next 2 are pretty nice on the next piecewise function. F of 0 is 2. I marked it. And -4 is 1. Those are nice, easy places to plot. The questionable ones get like f of -1. Thinking, man, is it 1 or is it -2? Remember, you're looking for solid dots. Holes are places where the graph doesn't exist. And then finally, f of 3 is 3. Awesome. And just for fun, I'm approximating what the equations of those might be. Let's say you're doing algebraically. So each of these has its own little equation. I'm kind of approximating, like the radical graph is shifted left 1, up 1. So I put little transformations on my square root graph in there. You don't need to pick that up just yet, but I wanted to jog your memory and say, oh yeah, we can move our usual square root graph by just adding values, +1 to the x and +1 to the outside of the function, makes it go left 1 and up 1. We got the bottom one, there's just y equals -2. So if we were to write this function out, and it would have those 3 components to it, and then we'd have to put the when domains that are associated with it. Okay? I think that's the end of my notes on here. Hope you guys are having a good day. I know you have questions on the practice problems, and I've seen some little errors here and there, and my math lab is kicking out some new issues for you guys. Some of you need codes. So if you need a code to get on my math lab, you can do it here in class. I have set these little red My Math Lab books. They're out on the desk, and they're in like a wrapped, sealed bag. There's should be 2. One code should work for 2 people. So if you happen to come up, share with somebody else. You're welcome to snap a picture of the code, but if you know 2 of you are going to use it wisely, and just grab one of those access kits, snap a picture, and do it at home. That'd be awesome. If you don't want to deal with that at all, I took some home with me, new ones, because I ran out last night, and you can just email me directly. I'll take a picture and send you a code that works. So you decide how you want to take that on. Other than that, do the best you can. Keys are posted in our online Drive folder. These notes are on our Drive folder, and all kinds of good stuff is out there. And make sure you look at, there's 3 folders currently, in our pre-calculus drive, so make sure you explore all 3 of them. The one that says My Math Lab on it is because every time I put an assignment up on a Google Classroom, it makes a folder for it. You don't have to put anything in there. It's just if I create an assignment, it makes a folder. It should be empty at this point. Okay, see you all very soon.